So we continue with the consideration of forces that are acting on a control volume. We did discuss and looked into the gravitational forces, but clubbed with it are the other forces. An important one of them are surface forces. So surface forces are not as simple to analyze because they contain normal as well as tangential components. So lot of things are taking into effect because of viscosity, the shear, and all these things that are playing their role when a real fluid is moving or is being considered. And therefore the consideration of surface forces is a bit complex as compared to the simple forces such as the gravitational force, which is acting only in one direction. The normal stresses normally are only the pressure forces. So pressure is acting on the normal to the control surface, control volume, and therefore that part is the component of pressure applied on the surface that we are considering. But at the same time, remember that when viscosity exists and it is non-zero, then the shear stresses are also, they come into act and they are also exhibiting, they are showing their presence. And therefore, we need to consider them as well. The gravitational force acting on a differential volume element is equal to the weight, and the axes have been rotated so that the gravitational vector acts downwards in the negative z direction. Well, we have shown here this is a small differential volume that we already saw in a control volume, but here it's an enlarged image that we see. And since the gravity acts only in the downward direction, as I have mentioned several times, therefore you see only this component that is non-zero, and we have to consider it. And of course, the rectangular coordinates, again, which I just mentioned a little while, they are mutually perpendicular and are known as Euler's coordinates system, and x, y, and z. So x and y are in the horizontal plane, while the z is in the vertical plane. And surface force acting on a differential force can be shown to be as d of f is equal to sigma ij dot n is a unit vector, times dA. So sigma ij is the crucial thing here that needs to be noted, and they are derived from the viscous forces and also that generate shear forces, and therefore they play a very important role in equations of fluid flow motion. Here, if we see a small controlled surface, and then you can see normal to the surface, we have surface forces as well. The tangential forces are the one that create this viscosity components represented by sigma ij. So they can also be written as, if we see two-dimensional force, then sigma xx, sigma xy, sigma yx, and sigma yy, and so on. So similarly, a lot of components are there that needs to be taken into account when we are considering the totality of the forces that act on a real fluid flow on a chosen control volume. The total forces, therefore, is summation of forces equals, and this is the net resultant force. They are comprised of body forces and surface forces. And in this we have the gravitational forces occurring here already mentioned, and for control surface we have sigma ij dot n times dA. This integral will take care of all the forces that are acting on the surface. This is the force that are acting on the whole body. And if we further expand it, then we will see that the surface forces comprise three main components. The ones that are normal to it are known as pressure forces. Then there are viscous forces that occur due to viscosity and gives rise to shear forces and etc. So the combination of pressure and shear forces will determine the totality of the forces that are acting on the surface. And in addition to that, we have written a summation of F other forces. If any other force also exists, we have to take into account. So the net total force is sum of all these forces on a real fluid flow.